All right. I wanted to share a couple of things with you in the back here. So, yeah, it's Tuesday the 6th. We're going to do a little CBPM and CAPM on an incline here, and I'll kind of refer back to some earlier understandings. Again, per your feedback on those surveys, I look at that. I try to find ways to do better. So, some of how that has manifested itself, I've got this now. The AP Physics needs to know. So the top thing here is the YouTube channel of AP Physics. So that's just a link that'll take you to what I hope will be the class channel. And I'm still trying to figure out how to use YouTube because it's only been around for your whole life. But here's a class from yesterday. Okay, I'm not going to go in and put a link every day to class. I just have this sitting up on top of Canvas that you go to the channel. And who was gone yesterday? Ethan was the only one? Okay. So they can just pop into this and
it's just you guys talking.
Okay. But what's kind of cool about it is I had the Pear Deck running. Even though I wasn't projecting it, so you can see some of the answers people are popping in.
And again, if you read the top of the screen, there are 4 points.
But like some folks have wanted like lecture notes or something like that. Well, okay, so then this is kind of like on here for you.
Okay. So one of the things I'm going to do is take this FU.
So anyways, long story short, I'm going to have to work on swearing less if I'm going to do that. But that'll just happen, so I'll just do it. It'll probably happen during 4th hour because you're the first AP class. So I'll try to catch it in here. And if it sucks, I'll re-record it 5th hour. And if that sucks, I'll re-record it 6th hour. But I'll try to just post one every day, maybe. I don't know. This is what my buddy Sarah does. So this is me trying to do this for you. And then later on in the year, when we get to exam review time, it's all there. So like when you need to go take a 30-minute poop during English class, you can just like bring your phone with you, pop in the earbuds, watch some physics, frickin' deuce, that sort of thing. But here's all the stuff that we got through yesterday, and particularly the stuff we did at the very end where we're finding the acceleration based on the FU. That's a good anchor understanding. So now that's there for you. You can just pop onto the YouTube channel. Ta-da. So I don't know what kind of bad habits that's going to create. And if it does, then we'll deal with it. But that's me trying something for you. Okay? What else do you need to know here? I don't want that one open. So today, Tuesday, I say skier here. It's not a skier, it's a box. Okay? This progression of problems on the sheet I'm about to give you is really important. It serves as a really important foundation for a wide variety of much more complex problems. I think it would also be helpful for you to remind yourself about our force flavors, so I linked that. And so that's available too. If you pop over to Canvas, you can see that. Some of our understandings about how forces are determined, how their directions are determined. Okay? Log in. All right, so with this sheet, what I'm looking for you to do is just kind of work on this as a group. So if you could grab a whiteboard from up front. And this first part of the problem, and if you want like a ruler or two, that'd be a good idea. The first part of the problem is an 80-kilogram box, and it's going to travel to the bottom of this 2-meter long ramp at a constant speed of 1.4 meters per second, and we're just going to model the heck out of that.
So we didn't come all the way up. I did that. I just
Nice.
And then John should like put on 2 plates for that.
Just chill out and go laser disc.
Oh, yeah, let's do that for sure. So yeah, hey, I never shared with you what the heck we were watching yesterday. Have you guys ever seen DVDs? It's how your grandparents used to watch Netflix. Do you know what a DVD is?
Yeah.
Okay. So back when I was your age, we weren't used to compact discs. So when they made video discs, they made them the size of what we were used to, which were 12-inch records.
Nice.
So behold the future in 1987. Laser disc. And so this is the
VHS is the VH bad.
Yep.
Everything's bigger.
Big circle needs a big remote. Yeah, we just had really bad eyesight back then, so everything needed to be a little larger. The hair, the laser disc, the 80s. All right. Yeah, cheers. There are more efficient ways of doing that.
Yeah, probably.
So, what are you doing? You're doing the sheet that's on the back projection here. I'm going to pass them out to you. You got a 80-kilogram box. It's going to travel to the bottom of a 2-meter long ramp with a constant speed of 1.4 meters per second. So the question is, which models apply? And then this is kind of that goal of problem.
We need
a little earlier in the year, you can do a goal of problem, but I assure you, this is a really important foundation.
Okay, this one? 80 kilogram box.
Is it right? Draw these programs.
So we got number 4.
Okay, so this is
Are you doing that?
It's funny.
Your headlights say 2048.
So we can do an FP. So it's constant speed.
CVPM, CPM, and BSPM, but not the
Constant speed.
HBDM,
Oh, FPDM. But what? Oh, well, yeah.
Maybe else be the sheet.
Yeah. And then we'll do HBD.
Yeah.
Cool.
Those are more
Oh, he's just
and it's still.
lazy such and such.
I think we need forward diagrams.
Yeah.
you want
It's like the thing that's like the,
Yeah, but we need four
all
models.
squares are
Yeah.
but not.
For diagrams. So FBD, HBD,
Cheers.
graph, and then another graph. There's another graph.
And it's all my bad.
Wait.
Okay, so
And then velocity.
I wouldn't do draw these.
I would do velocity.
Oh, sure.
Draw like, I don't know. So draw a position over top.
And then what's the last one?
We can do motion. You can do the motion. I'm not from
They don't help
4
me.
meters this time.
Who's reading my diary? Oh.
I feel like that's how everyone's diary starts.
Once you're done, rather than playing Pokemon on your Chromebook, Riley, or Tetris, Jared, go ahead and take a look at the next problem. Hey, let me explain how this sheet is a progression. You're starting from this initial situation where it has a constant speed, okay? After that, it's varying the amount of friction. So you know how much friction there was when there was constant speed. What happens if we change that friction? So in part 2, it's only 150 newtons of friction. So think carefully about how that would impact things, okay? You can work on that on the sheet, kind of think through that on the sheet a little bit. Now that you know how it works when it's CVPM and the forces balance, how does it affect all those quantities you just determined if now the friction were only 150 newtons, okay? So groups are finishing up their boards and bringing those up front. The rest of you are pushing on to problem 2 and being purposeful with your time. The benefits of sitting in the front row. Look at that. Just do that.
Okay, I think it went away, but there was like 3 that was like shaky, but there's a bonus question that was really easy. So you get one.
Ben, you're bad.
Everyone's actually good stuff.
What else?
Yeah.
Hey, other things I should mention. The final coming up. on Thursday is CDPM, CAPM, so I put together some things like, I know you get made fun of sometimes for being tryhards by me. And so I tried to find a way for you to practice some of these physics understandings that are gonna show up on that final without like your friends knowing that's what you're doing. Like, hey, I'm cool. I'm playing video games on my Chromebook during class too. This one's called Graphs and Tracks. And basically you're trying to set up the situation down here so it matches this graph. So there's a position versus time graph. Clearly I know what about the initial velocity from the shape of that graph. That's the position versus time graph. Clearly I know what about its initial velocity from the shape of that graph. AKA it is. Now, all right. So I'm gonna give it an initial velocity that's negative, and then I can roll the ball. But I gotta find a way to get the velocity to change. I can do that by not making it not that big. We can try it though. Let's see. Oh, that didn't work. Hello. Okay. There we go. Did it do it?
This is difficult.
Let's try that. Ooh, that ain't it. And let's go with this. Ooh! Yeah! Okay? So what do I need to do? What do I need to tweak about the situation to get the graph to do that? Okay, so the thought is, this will kind of work on your understanding of how these things go. Now, I'll just warn you, maybe you picked up on it earlier, the velocity versus time graph is really the key to all this stuff. You can switch this so it becomes velocity versus time graph. And then that might do a better job of helping you understand what you need to change to get this to work right, okay? But that's some practice, and then the other thing is this thing called Waker. And unfortunately, you got to get Flash in order for that to work, and it's probably going to want me to like right-click something, and I can't do it. And you might get all the way through this game and not realize you were doing physics, but okay. So anyways, you can go check that out. All right, did I stall well? Almost. Yeah, come on, man, get me there. All right. So dig this. You got this little kitty thing, and you're trying to help the kitty get to the ball or something like that. Let's try it. Let's start. Today in class was great. Mr. Harding wouldn't let us play video games, but he did. So I'm just using arrow keys here. Ooh, space bar doesn't jump. What jumps? Oh, button jumps. There we go. Nice. Kitty, go kitty. Go kitty. Go kitty.
Terrible.
Go kitty. Ooh, D button. Go kitty. What does D button do? Oh, kitty made a graph. Kitty can use that graph. Whoa, whoa. Graph, kitty, graph. Wisp of pain. All right. I got more wisps than you do. So anyway, so those are things you can do so that your friends don't know that you're trying to get ready for the final. Okay? All right. Just about there.
Well, I don't know how that would be 2-7.
Was he trying to box up something really high?
Yeah.
Volleyball is like 6 feet high. He tried to do it. And he tried it. And he couldn't do it. I was like, you can't box.
It was the first.
No, 6'5".
That was for you.
Or you can come up and do that.
How good is that?
All right.
Well, yeah, but
He's not, I don't.
So I found some volunteers to come up and talk to us about model choices. That's the first part of this. What are the appropriate models? And then that kind of helps you establish which tools to use. All right, so which models apply to the situation and why?
Okay, well, it's constant velocity, which implies constant acceleration. It's explicitly stated to be constant velocity, and it also implies VFTM. The forces are balanced. It cannot be VFTM and UVFTM, so it's only VFTM. Yeah.
There you go. So it explicitly talks about the fact that there is a constant speed here, therefore it's CVPM, therefore it's BFPM. All right, thanks, lads. Go ahead and flip another board to talk to us about part B, one of the 4 graph and/or diagrams. Hey, come on up, group 1.
All right, so in this model here, had the velocity over time. We had 1.4 meters per second over the whole duration of the ride that box went on.
Okay. We're going to kind of combine part B with part C. And I'm going to do something else here too. Okay, this is something else I figured out the other day. I'm going to run a pair deck as a back channel here for you to ask questions. So this is my version of Freeze's parlay. So I've just got an untitled presentation that I'm going to start presenting. And this is where I want you to go ahead and ask your questions. Okay, so this is at WCHCE, this is joinpd.com. And Eddie's group have shown you their velocity versus time graph with the 1.4 meters per second. And I guess what I'm looking for you to do here is ask them a question to see if they can find anything else to put on that graph.
You're going to do that now. Nice junior.
All right, just a second. I gotta ask. Boop. All right. Not a numeric answer. That's not the button I meant to hit.
Enter a number.
Boop. All right, text. So use pair deck, and you can kind of ask them a question.
Question asked is what is your question? And your answer is your question.
They've got velocity versus time graph. They've got the 1.4 meters per second there. Should they be doing anything else with that? So I've got this thing running with the screencast up here. I'll just have the pair deckage open here. Let's see if we can make that happen. Yeah. All right. Okay. So let's see. Do we know more values on the velocity versus time graph than just that 1.4 meters per second? Mom? Also, how much time passes from the start to when the box reaches the bottom? Is there a way to figure that out from the velocity versus time graph? So I think, in other words, they're asking you, is any of this additional information that we have, the 80 kilograms, the 2 meters for the length of the ramp, any of that would show up on the velocity versus time graph?
Oh, yeah, the 2 meters is like the area. And then you can solve for time.
Okay, so if that area is 2 meters, what do you want to ballpark? Could you ballpark the time?
We meant to include that in problem B? I thought that was all in C.
We got
They're-
1.4 seconds.
They're kind of all
I see.
interrelated. So the height of that box is 1.4, so therefore the base is going to be
No, the base is like 1.43.
1.4 seconds.
Yeah, it's like
Okay, cool. Right, so that's how root 2 works. Okay, so that's what we're looking to do here. Not only so if we put part B and part C together, figuring out values on those things. So there's their velocity versus time graph, and that's how they could use it to figure out the time this thing's in motion. Okay, thanks group one. Go ahead and flip another board to talk to us about something other than the velocity versus time graph.
Let's go.
All right, so we talked about the velocity versus time graph. Is there anything else you drew that you found helpful?
We have a free body diagram with
Okay.
all of the forces acting on it. There's gravity, friction, and push acting on it.
Okay. Can you just walk us through your choices on like how many arrows there should be, what the flavor should be?
Okay, so since it's DPM, the forces balance out, and there's always gravity, and there's huge push because it's on the surface, I guess, and friction's acting on it.
And why friction? I guess that's the one I'm particularly interested in.
Because it's large enough to where it matters, I guess.
Okay. Because of how this thing is, like, what is it about the problem, I guess, that clues you in there's friction?
It's a box. So
And it is,
rather large, the surface area. It's large. It's on ramp.
and it's on a ramp, but it's not getting faster as it slides, correct?
Yeah.
So it's sliding down an incline, but it's not speeding up. So it's like sledding at some less exciting high school sledding hill, right? Like here at Westside, we get faster, but Liberty, have any of you ever gone snow sledding at Liberty? It's so sad. There are no hills. Yeah, you just sit on your sled basically. Look at all the pretty bricks. Okay, cool. So that's a free body diagram. Go ahead and flip it. Let's see if we can find somebody to talk about something other than the velocity time graph and the free body diagram. All right, root 2. Oh man, root 2. You should have gotten to talk about the velocity time graph. That is your time to shine. So free body diagram, velocity time graph. Anything else you drew that was helpful?
Well, we did a different schema and the headlight diagram.
Okay, what helped you? Which one helped you find stuff?
Probably like a combination of the headlight diagram and the force diagram.
So chat us through that. How'd you figure out some unknown things?
So what I did was I just drew the force diagram, and then I used some fancy vector addition techniques.
Are you talking about putting arrows together?
Sort of.
Okay.
And some trig to basically just find this angle and these values. So I got a friction force of 273 newtons and a normal force or a smoosh force of 752 newtons.
And can I ask you to be a hero? Your arrows right now kind of look like dashed lines. Can you show the directions of those things?
Well, this one is actually just going that way, and this one's actually just going that way.
Because yeah, you can see them in the free body diagram, but just also make sure you include the direction in the force addition diagram, or the HPD as it were.
So yeah.
Alan, are there tips on those arrows now? Yeah. Okay, I can't see from here, but I'll trust you. All right, good deal. So you can see how the friction works there and how the smoosh poosh works as well. Cool. Thank you, Root 2. Is there anything else we need to know? I think that's about it, right? So we figured out the time, we figured out the smoosh poosh value, and we figured out the friction value. Okay. So thanks, lads. And let's see how that agrees in other groups. Oh boy. All right, so it looks like a smoosh poosh of 624 and a friction of 227. Here we got a smoosh poosh of about 750, a friction of about 270. smoosh poosh of 752 and a friction of 274. Simon mentioned the fact that this is a right triangle. Why? Because like how and why should we know this is going to set up as a right triangle? You've got gravity, Quinn.
Because the friction force and what you call smoosh poosh they're always going to be perpendicular to each other.
That's our
If
understanding.
if you just hook it up to the hypotenuse, which is the gravity, you get a right triangle.
There you go.
Okay.
So kind of know that about the circumstances here. Smoosh poosh is going to be perpendicular to the surface. Friction is going to be parallel to the surface. So we can kind of know that going in, that this is going to orient as a right triangle. Inclines that way. So you might draw the friction and the smoosh poosh. And if this is 90 degrees, and again, friction's parallel to the incline is 20 degrees. Okay? I'm being dumb. Give me a sec. I should be making this happen. All right. There we are. So FG is going to be down like that. You're going to have your friction like that. And you're going to have your smoosh poosh like that. 90-degree angle here. Okay. And then trying to establish what the angles are inside. If I am big in this. This is the angle between the friction and the horizontal. That's going to be the same as the angle between the surface and the horizontal because the friction's got to be parallel. So that's how I know this is 20 degrees. And then who's got a calculator? What's this angle going to have to be? All right. So then if that's 70, this has got to be 20. And like Simon said, gravitational force here is how many newtons? 800 newtons. So then I can just do a little bit of trig. We could do a little law of sines or something. I don't know how you people like to write law of sines, so I'm just going to do it this way. 800 newtons over sine of 90 equals the force of friction over the sine of the angle that's opposite it. That would be 20 degrees. Equals the smoosh poosh divided by, the tip on this thing's about to break off. If you look on the diagram here, the 70 degrees is the angle that's opposite the smoosh poosh. So you just bust out some trig, okay? If you don't want to do it the scale drawing way, you're more than valid to use some trig here. And 273 or 4-ish for the friction. Don't break off. And then this is 750-ish. Cool. Okay. And then what were some of the other things you people drew? Certainly the velocity versus time graph. This is 1.4 meters per second. And then we know that this area here represents the change in position. And so then you're just doing area rectangle equals base times height. So 2 meters equals the base times the 1.4 meters per second. And that's how the time equals 1.4 seconds. All right. So now that we have the CDPM case sorted out, don't erase this board, okay? Just revise this board. The only thing that you're changing about the situation is you're making this friction arrow a little bit shorter. You're making this friction be 150 newtons. Okay? This friction arrow is now 150 newtons. How does that change things? Okay? So grab your board. Please do not erase the whole thing, but just change that friction arrow to only be 150 newtons. Right? Is that what it says? Yep. Ooh, lasso tool. Where's the lasso? Okay. So hey, if you smell me here, I'm coming into this diagram, and this arrow that was 250. How much was it? 273, right? This was 273. Now it's only going to be 150.
It's no good for it. Stay there. And so then we get net like there, right? Mass. Very bad arrow. Edgy too. Yeah. That is 270 or so minus 150.
In that case, they just want to be closer in that swamp. Yeah. No, but the angle has changed.
So then we can find acceleration because
And the angle has changed.
and we know
So we can
M
still
is
find
800.
Yeah, so we changed it. We still know.
800 times acceleration. It's 800. 800.
Yeah.
Mass is 80.
Still
80. I'm
Yeah, 80. Yeah. Still
I am 80.
Or
So please go ahead and amend the things on the board that need to be amended. If your velocity versus time graph should change now, then go ahead and do that. Keep in mind it says this 80 kilogram box, hey, this 80 kilogram box starts from rest and travels to the bottom of the 2 meter long ramp, but its motion is opposed by 150 Newton frictional force. So I guess I shouldn't say the only thing that changes is the friction. Also, the initial condition changes. This thing is starting from rest, so use what you can from the numbers given to figure out as much as you can here. It does start from rest. Yeah, sorry.
Okay, so
Dynamically, the only thing changing is the amount of friction is less.
Yeah.
change that one.
No, that's the same. Drops 2 meters. That's fine. Reach like just go like the normal velocity when it's accelerated. The slope here is 1.5. 2 times. That's backwards. Reach.
The ramp's going to stay the same, so the incline's going to stay the same. So I'm pretty sure that was the same. You said it's fine.
It's beautiful.
2 equals
Wait, area. Oh, wait, it's AT squared.
So mass, what's if you're getting like mass over
4. So we need to find the slope of this guy.
T squared.
I'm pretty sure that's going to be the same.
Anybody want to do that?
So it's 2 What is it?
2 divided by the square root of 1.5. Otherwise, 4 over 1.5. Then the square root.
Okay, so then 1 point.
Okay, so I'm still at about 1.6.
Type of graph? Oh, you haven't fixed the graph yet, right?
Oh yeah.
We fixed this one. This is
What is that?
still velocity.
Okay.
It says velocity.
Oh,
Kind of.
I thought that was a drawing of a buffalo from a French cannon or something. But, you know.
I can see that.
Sports ball. You want
1.5, and so we know area under. No, we don't know area. We know.
Again, as I'm looking at some of your graphs, keep
Area
in mind, it
under
does explicitly
acceleration.
state in the problem this thing starts from rest. So you still have that question up top. Determine which models apply,
No, this is.
and then you're drawing at least 4 diagrams and/or graphs to represent the
No, this is
situation,
times.
and
this is
determining
times.
what other
Yeah, that
quantities
is-
you can solve for that are not explicitly stated at the beginning.
There you go.
3.
Yeah.
Try anything else?
No, I don't think so.
Alright, we got the question right there.
Yep.
We're done.
Beautiful.
Okay.
What'd you get for acceleration?
Oh, we need to choose the equation.
So does it go all the way down the ramp?
Did you guys pick your?
Yes. Yes.
Yo, stay in your lane,
Okay,
Red.
272.5.
What'd you say for FU? Riley.
272.5 minus.
What are you doing? That's their board. You get one board. They're good. They'll figure it out.
It's 130.
So,
I think we should just get this.
It's not a mistake. So we need to find the. We need to find the slope of this guy.
Find the FU equation.
What do you
Well,
guys
we need the slope of the supply.
anyways, we're good at this, right?
We have 2 equations? Yes, we do. We do that one and that one.
And this one.
Probably
Somewhere over here.
Do not repeat a derivation.
Because then it's
All done.
1.5 times 63.
originally it's 272. It's not
Don't worry about it.
all that.
Triangles.
Okay, we can use the thingy.
Yeah. Well, I want Josh
Right.
We don't
We don't care about that.
Wait, no, do we need to?
Go ahead.
Oh, okay.
So that's 123.
I mean,
But he's got to take.
So what was this? 270.
It's 273.
Yeah.
So
okay, so
Hey, do try to write really small too, so it's hard for everybody to see what you're doing on your board. That'd be great. Or clutter it with a lot of stuff.
there, and then we can find it.
like that.
Then we can find half.
That's good enough?
Wow.
Okay.
I recognize that from Paradigm yesterday.
I enjoy it.
Friends, try to expedite so we can hopefully present this last part before we bounce. And I should say, it's not the last part. This is part 2.
Oh yeah, it's been super.
I get this thing. It should be like 7. You don't know how long? No, but it's hard to find it.
Yeah, well, basically you should.
Hey, injury.
Again, for those of you that are done with part 2, a good use of your time would be to push on to part 3, where again, you're not throwing it out. Whoa! Where'd the friction go?
I ate it.
What happens in this diagram if there is no friction, and how would that affect your answers? So this is only 150. So how far away is it from being able to close up?
I'm really not sure that's right.
Well,
I mean, we really don't have that.
Not it.
I don't want to talk either.
Where we don't have units on these.
No, I mean like not a.
Yeah, not that.
It's okay, so this is 1.55. Okay. That shows up there, but it shows up anywhere besides.
What was the SPM?
Wait.
You know what Yeah, I feel
We
like
did it right. That's how you find it.
Oh wait, that's what sound like 260.
4 divided by.
Wait, so we know the friction and the are
Every area does.
the space is same. Yeah, I think.
Yeah.
That's 4 divided by, yeah.
Or you calculated.
That's supposed to change the side of all.
1.9.
here.
So then times our acceleration again.
Right, so put in calculated.
I'm
just trying to think of the reason why that one is.
All right, youngins, we're about to date. So store your boards from today. Hey, if you're still working on the part 2 board, I need you to take some time outside of class and start peeking at problem 3, because the groups that already have their boards up front are already well into problem 3, and I don't want to have them wait a bunch tomorrow. So that's my expectation. Show up tomorrow with at least some notion of what the diagrams are going to look like, even if you don't have the math crunched out for part 3. If your board's up front, go ahead and snag it, store it in the back there, and we'll pick up with this later.